Hello everyone, welcome back. This is lesson number 4 on continuity. In the very first video, we talked about the 3 criteria that you need in order for a function to be continuous at a certain value of c. And then we did 4 examples writing out what you need to write out to see if it's continuous or not. In this video, we're going to talk about 3 examples where you're going to be given some variable that represents a constant or variables, and we got to figure out what value of a will always make this continuous. Okay, so what I want to just do really quickly is look at the fact that 1 for continuity would be f of -1, and remember we're looking at the equal sign right here. That's going to be equal to whatever x is, so we plug it, it's -1, right? So we're using this function right here. So f of -1 would be equal to x, which again, when you substitute in, we get -1. So what we really care about, though, is this next step, is the limit as x approaches. And again, because it's greater than, we were going to use a right-hand limit. You want to say that x approaches -1 from the right of x, which again would be -1. And we're going to say that the limit as x approaches -1 from the left, and this is a left-hand limit, right, for less than, it's going to be equal to, well, we're going to go ahead and plug in, so it's going to be ax squared plus 2, but we automatically know what x is, right? It's -1. So it's going to be -1 squared, which is 1, so it's just going to be a plus 2. And this is totally legit. It's a totally way of just saying this, that yes, a limit can be an expression. What I do not want, and what students typically end up doing, is they said, okay, let me just go ahead and set this equal to that. You don't get any credit in calculus if you do that. If you just set x equal to ax squared plus 2, we're going to ask you guys why. Why are you doing that? Why are you doing it? Well, what is the reason why you're doing that? We want to make sure that the left-hand limit of our function is equal to our right-hand limit. If that's the case, right, then we know that this limit will exist, right? And we also want to make sure, because we want to prove that it's continuous, we also want to make sure that both our limits are equal to -1. So now what we're going to do here is, well, the left-hand limit, this is going to be ax squared plus 2, and this is going to be, our right-hand limit is going to be -1. All right? Now we already know, based on this, what was our left-hand limit. So I should have actually just went ahead and skipped that step and said it's just a plus 2 is -1. And so a is very easy to solve for. Again, this is to meet -3. So once a is equal to -3, so let's write that out. So if I look at f of x, and I look at it as -3 x squared plus 2 and x, then I now have a function that's continuous everywhere on our continuum. And I already know that it's continuous everywhere other than x equals -1, because both these graphs are polynomials, right? So now if I plug in -1 here, I get -3 plus 2 is -1. I'll plug in -1 here, I get -1. So now I know that I'm continuous everywhere. So the answer is -3. So you need to make sure that you guys write out these steps here while you are solving the problem. So you want to make sure that everything that I'm circling this weird way, that this is also part of your work, okay? Because you got to say, well, the limit's got to equal, the left-hand limit and the right-hand limit have to equal each other. So that's what you have to do. So let's look at the next example and see what we can do with that one. Now this one's a little different because it says find the constant a so that the function is continuous on the entire number line. So this one's not an inequality. This one right here is going to be a less than, it's going to be a not equals to or equals to sign. So the first thing that we look at is that f of a is going to be equal to 8. Okay, so f of a is equal to 8, and that's pretty straightforward. Then when we do the next part, we want to say the limit as x approaches a of x squared minus a squared over x minus a. So we don't necessarily know what this function looks like, but if we do direct substitution, which is always the best bet, then you can get 0 on the top and you're going to get 0 on the bottom. So this goes back into the fact of what we talked about in lesson number 3, is that I can simplify this a little bit more because we have 0 over 0, which is an indeterminate function. So, or it's an indeterminate form, I should say. So the limit is x approaches a. Well, I'm going to factor the top, Like you guys can see, as the more videos you see of this, they always relate to each other, right? So now we're doing something that we learned back in lesson number 3. So we want to cancel something out. Now again, this only applies because it's 0 over 0. If this had been 0 over a number, then the answer would be 0. Your limit would be 0. And if it's some number over 0, then it does not exist and it's not continuous at all. And the question wouldn't work out well at all. And so if we look at this, we're going to say now that this limit as x approaches a is x plus a. And it's okay, it's x plus a. And it's okay that it's a variable, so we're going to substitute in, direct substitution in, and we're going to get a plus a, which is equal to 2a. Okay, so for this example, we need to make sure that we showed what f of a is. We also need to make sure that we showed what the limit is. Because when we get to step number 3, in order for it to be continuous, f of a has to equal the limit as x approaches a of f of x. This is the definition of continuity. So if you're not following along pretty well with this, then make sure you go back and learn what the definition of continuity is in the first video, because again, the point, then the limits, and now this. So now that I've said what I've written in green, now that that's actually written on our paper, we can now say, well, what is f of a? Well, f of a is 8. What is this limit? This limit is right here. It's equal to 2a. And then our answer is obviously going to be a equals 4. A equals 4. And so I can go back and rewrite this as f of x is equal to x squared minus 4 over minus 4 squared, or x minus 4, where x is not equal to 4, and 8 when x is equal to 4. And now it's continuous everywhere. So yes, x squared minus 16 is probably what most people would want to write right there. And then you guys would do, and you've done problems like this before in our classes already. We've already showed you examples like this. You don't have to rewrite it, it's just that this is now what it looks like for all continuous functions. All right, let's do one more, and this one's going to be where you have 2 variables. So we've kind of showed you an example of each type right now. This is one with inequalities. So for inequalities, our main focus is just on limits, just showing that the left-hand limit equals the right-hand limit. If it's an equals to or not equals to, then you need to go through all 3 steps and show all 3 steps. And then let's look at example number 8 and talk about that one now. Number 8 says find the constants a and b, so both of these, a and b, so that the function is continuous on the entire number line. So since you see we have inequalities here, our focus is going to be on limits. It's going to be on the limit part of this. So I'm going to look right now at x equals -1, and we're going to do that one first. So if we look at -1, this is less than, so this is our left-hand limit for -1, and then x is greater than -1, this is our right-hand limit. So we can take the limit as x approaches -1 from the left of 2, and based on our limit laws from the last lesson, we know that this answer is just going to be 2, right? Whenever you take the limit of some value of a number, it's always that number. And then the limit as x approaches -1 from the right is ax plus b, right? That's the function we plug into. And we know that x is -1, so I'm left with -a plus b. Okay? And so from that, since the left-hand limit has to equal, in order for it to be continuous, the right-hand limit, now I can set 2 equal to -a plus b. And I can go one step further and say, okay, well, b is just going to be equal to a plus 2. Okay, a plus b. b equals a plus 2. Now, if I go to the next step with x is equal to 3, so we're looking at that, the limit as x approaches 3. Now, this one, let's say x is less than 3, right? Less than 3, so that's a left-hand limit. So 3 from the left of ax plus b. And we can go ahead and plug in 3, so we're going to get 3a plus b. And then if I look at the limit as x approaches 3 from the right, well, again, this is right, greater than, is a right-hand limit of -2. And again, the limit as x approaches anything of a constant is just that constant. And then I can say that the limit as x approaches 3 from the left of our function must equal the limit as x approaches 3 from the right of our function. Now I can say that 3a plus b is equal to -2. And I've got two equations with two unknowns. And that goes back to good old Algebra 1, Algebra 2. So I now know that I can say that b is equal to a plus 2. Well, here is our b. So I can say that 3a plus a plus 2 is equal to negative 2. And just like our system of linear equations, now we can solve for this. We get 4a is equal to negative 4, so a is going to be equal to negative 1. And then we're going to substitute back in, since I now know that a is negative 1, then I can say b equals negative 1 plus 2, so b is equal to positive 1. Positive 1. So a would be replaced with a negative, and b would be a 1. So I would have this rewritten as negative x plus 1, and then we would have it continuous on all values of x. Okay? So that's what you would have to write out for that. So inequalities, let limits be your function. I know students are like, well, why didn't you write the f of negative 1? Why didn't you write the f of 3? Yes, those are true for it to be continuous. Okay, but the reason why I didn't write them in this, and you can absolutely if you want to, but I want you guys to know that if you were to go back and look at this question a little bit better, if you wrote, since this is less than or equal to, then f of negative 1 is going to be equal to 2, and this, since it's less than or equal to, where I'm defined is also going to be equal to one of my limits. So since one of my limits, I'm comparing these two limits, I know that all three of these have to be equal to each other. And I don't know if that's making sense to you guys, but hopefully it is. So you don't need to write them down, but you can absolutely write them down. So for example, f of 3 is equal to negative 2. Well, that's already going to be equal to the right-hand side. So the bottom line of what I'm trying to say here, if you guys have not zoned out of me as I'm zoned out of myself here, is that I didn't write these two things down because I'm not showing continuity. I'm not doing what I did in the first video. I'm finding values that will make it continuous. So I'm not proving if it's continuous or not. If I'm proving it's continuous, I need these two things to do. But if I'm just trying to find constants, I need to figure out what's going to give me these values. And if it's inequalities, it's limits. If it's not inequalities, it's equal to or not equal to, that's when you have to show this other step. So bottom line is, if you're not sure to write it, just go ahead and write it because you will not lose points for extra information. Okay, so I think with that, that's enough being said about this video. I hope this was helpful for you guys, but let me know if I can help you guys out in class and stuff like that. But here we go. That's video number 2, and we're going to come back and do a really easy graph problem with continuity, and then our first FRQ. So it's really exciting, which is a free response question. So I'll see you guys in the very next video.